Okay, good afternoon. Welcome to EE222. Yes, what were we looking at yesterday? We were looking at this particular problem, right? The problem is to go through. By the way, if you look at the tutorial, there is also some design problems in the tutorial as well. So this is an in-class problem for week 11. So it says we have to go through this particular cycle 1, 3, 5, 7, 4, 2, 0, 6 and repeat, and it's in one direction. So if you look at our earlier design problem, the earlier design problem was much more difficult. So first thing you do is you draw a preliminary state diagram. You can draw it in decimal, right? Now the type of machine which we are building over here is known as a sequence generator. Sequence generator, right? Okay, so it's a sequence generator. It outputs, the system will output those particular sequences. All right, now the next thing was the largest number in this particular sequence is the number 7. When we convert 7 to binary, we get 111. 111 means that you have to occupy 3 bits. 3 bits means 3 flip-flops. If there are 3 flip-flops, that means there are 8 possible states. If there are 8 possible states, how many declared? How many used? 8 used, so therefore 0 unused. So this becomes an easier problem. The one which we did earlier on, that's a difficult problem, because even though it was only A, B, C, there was, so the largest number, and then we worked out, oh, there's one unused bit, right? Okay, one unused particular combination. Okay, now, what is the next step, guys? What is the next step? Right. So we redraw, so let's put today's date here. Today is week 11, lecture 2, and today is 8th June. Okay, now what we have to do now is we need to redraw the state diagram in binary. So let's have a look. 1, 3, 5, 7, 4, 2. So 1, 2, 3, 4, 5, 6, 7, 8. So what's the number? 1, right? Firstly it started off with 1, 0, 0, 1, 3 is 0, 1, 1, 5 is 1, 0, 1, 7 is 111, 4, 0, 1, 0, 2, oh, sorry, 4 is 1, 0, 0, right? We're having a look over here. 4 is 1, 0, 0, 2, 0, 6, 2 is 0, 1, 0, 0 is 000, 6 is 1, 1, 0, and it all goes in that direction. From the question, if you look at this question, guys, Okay, let's look at, if you are missing from yesterday's lecture, this is where the question comes from. Right? This is where the question comes from. All right, now, if you look at the question, there was 8 states, 1, 3, 5, 7, 4, 2, 0, 6, and that's exactly our sequence. There is no reverse sequence. Now, when you look at the question, guys, once again, when you look at the question, what can you tell me about system input and system output? Is there any system input? No, there's no system input. Is there any system output? No. So this is a much easier problem than our previous one. There is no system input, there is no system output. So that gives us like, it's almost like a bonus. All right, so let's now draw the next step, which is step 2, which is the state excitation table. Guys, when you are designing, we use the name state excitation table, which means you've got to use the excitation table, right? It's the state excitation table. All right, there's no system input, so instantaneously we go to, let's call this here, let's call this, you can name it anything, guys. Let's call it, just to give you an idea, let's call this Q0, Q1, Q2, right? You don't have to be Q2, Q1, Q0. Look at this, I've given it a naming convention, so long as I'm consistent. In my previous one, I was calling it QB, QA. You know, sometimes you can call it Q2, Q1, Q0. Doesn't really matter. So long as you are consistent. Okay? All right, now, so we've got 3 bits. We have Q0, Q1, Q2. What comes in next, guys? So this is the, and you've got to use a ruler. You've got to use a ruler. So what is the next state? No, sorry, flip-flop inputs. You will have flip-flop inputs, right? So I'm not. Did the question say what we have to use? Okay, let's use. What do you want to use? SR? Okay, our friend saying SR over here. So this is your current or present state. So S0, R0, S1, R1, S2, R2. Right? Everyone there? Okay, and what do we finish off with, guys? Q0 star, Q1 star, Q2 star. And what do you call this? Next state. There we go. All right, guys, once again, look at this state table, right? Are there any system input? No need, because there wasn't any system input. Is there any system output? No need, because there's no system output. So this is a very, what you call a plain vanilla, state table. No system input, no system output. Everything flows in one direction. All right, so what do we do over here on the input side, the first 3 one? You populate according to all possible combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. Okay? All right. So, all right. There we go. Right? Everyone can see this. So I've populated it on that side. Right? I've populated this on that side. So everyone happy with that? Okay, now, based on our state diagram, we've got to predict, we've got to fill out this side. So what people do, guys, is sometimes they take these three columns and they put it here, and they take the flip-flop inputs and put it here. That's okay. So long as these three, the present state and system input, must be first. Must be first. Must. All right? That's how you'll populate it. You can take this section, put it here, take that section, put it there. That's fine. Right? Okay. System input and present. System input and present state must be first. All right. Now, let's now fill up these guys. All right. Let's fill it up. Okay. Let me zoom out. I hope you have it all on your same page. Radio 0, 0, 0 becomes, right, you call it out, all right? You guys call it out so that I can write it down. 0, 0, 0 becomes 1, 1, 0. Right, next, 0, 0, 1. Look for it. Next, 0, 1, 0 becomes 0, 0, 0. 0, double 1. 1, double 0. Sorry? Okay. 1, 0, 1. 1, 1, 0. Triple 1. So did you see? So that was a good one. All you do, so if you look at it, this table and that one is the same thing. Except for in this table, you have your flip-flop inputs. Now, you have your present state, you have your next state. Tell me, which flip-flop will we use over here? Which table? SR. Now, which table will we use? Excitation or characteristic? Excitation. All right? Why excitation? You have your present state, you have your next state, you want to determine what your combination of input should be in order to drive your flip-flop in that direction. Everyone with me? Okay, now, let's now follow. You have to have a ruler, right? I forgot my ruler. Okay, there we go. And you have to do like for like. Q0 is 0, Q0 star is a 1. What do we get? What is our S and S0, R0, guys? Come on. Huh? Okay, 1, 0, all right. Next line. Q0 is a 0, Q0 star is a 0. What do you get? 0x. Okay, next one, 0, 0, yeah. What do we get? 0x. Guys, you can see the board, right? You can see my writing, or is the light affecting it? There. That's better? Okay. 0, 1. You guys know where to? Anybody stuck with the excitation table? Anybody stuck with the excitation table? Doesn't know how to read the excitation table? Right? This is your chance. Okay. Now, 1, 0. 0, 1. Okay, let's speed up now. 1, 1. 1, 0. 1, 1. Let's move to Q1. 0, 1. 0, 1. 1, 0. Huh? 1, 0. 0, 1. 0, 1. 0, 1. Sorry, 1, 0. 1, 0. Okay, let's move to Q2. 0, 0. 1, 0, 1, 1. 0, 0. 1, 1. 0, 0. 1, 1. 0, 1. 0, 1? 1, 0. Okay, now that's our state table. Done. Done and dusted. Now the next step is, we've got the table now, we've got to find the Boolean algebraic function. Right? We've got the table now, we've got to find the Boolean algebraic function. So step 3 is find Boolean equations for the flip-flop inputs. So we have to use Carnot maps. Let's start off with, what was it we started off with? S0. S0. So how many inputs, guys? Let's look on this side here. So if we look at this table, we forget about all of this. Forget about all of these guys. Right? So it's just a 3 input and 1 output. That's what I'm saying. So how are you going to plot that? You're going to use a Carnot map. Or if you're smart, sometimes, you know, what other ways you can make a function? You can do sum of products, product of sums. You can do Boolean algebra. You can even do multiplexer. You can use a multiplexer. So it doesn't really matter. You can even use a multiplexer or a decoder to get the function. Right? Yeah, I mean, you don't have to have AND OR function. Well, that's what I'm trying to say. You can do multiple things to enforce that input into the AND gate. All right, so 0, 0, 0. All right, okay, so call this out, all right? So we have okay, and what is our inputs? Q0, Q1, Q2. Q0, Q1, Q2. I like to put it in the same order for convenience purposes. Nothing, no rule. You can do Q0, you can even make a vertical Carnot map, no problem, no problem. I like to do it so that, you know, it's very easy for me to copy. Now, can you call out this? So look at this, 1, 0, 0, 1. 1, 0, 0, 1. Right, 1, 0, 0, 1. 0x, 0x. Look at this. I come here. You have to know the sequence. 0x, 0x. Set? You see how I did that? Right? I filled it up. Because now you should be a pro at Carnot maps. Right? You should know which cell is where. Okay? Now, what groups can we make here, guys? Any way to do it? Anybody got anything different? You can do it in your way. Don't have to copy me. Remember, I make mistakes frequently on the board. Right? And this is the funny thing. Sometimes I even make mistakes on that YouTube channel. So please be careful. You might have to check. All right? Okay? Now, is this correct? Anybody audited my work? Okay. Now, yesterday I took the tutorial. I took one of the tutorials yesterday. And we were doing a problem. And then we made mistakes. We had made mistakes over here. You know, when going from the truth table and all this kind of thing. And then because this is going to be there's mistakes here, that means there's also mistakes here. All right? So please be careful when you do this. All right, now, let's now group it up. Let's make that into one big group, and that's alone. Right? So what do we say, guys? What do we say for this? We say S0 is equal to, what is it equal to, guys? Q0 bar, Q1 bar, Q2 bar. Or, what about this guy? There'll be Q1, Q2. Done. Let's do R0. Right? We can do it very fast. 0xx0. 0xx0. 1010. Set. Did you see how I did that? Okay, because you know the cell numbers. All right. And you know the sequence. You know it's always going to be like this. 1, 2, 3, 4, 5, 6, 7, 8. Yeah? All right, now, what do we get, guys? Any groups, any groups, any groups, any possible groups? Oh, only this guy, right? So what can we say? We can say that R0 is equal to, yeah, Q0, Q2 bar. All right, let's do the next one. S1. R1. Let's fill it up. 1, 1, 0, 0. 1, 1, 0, 0. Let's do the other one as well. R1, 0, 0, 1, 1, 0, 0, 1, 1. What is S1 equal to, guys? This one, R1 is equal to? R1 is equal to? Q1. Everyone with me? Okay, this is the pace at which you should be working in the final exam. If you start going and doing, okay, 0, 0, 0, you know how I teach you guys, you know, in a very slow pace. If you start doing that in your final exam, right, you will fail the exam. You've got to know, you've got to have enough practice to be able to, you know, because to be able to fill out Kano maps at a very rapid rate. Okay, I just look at the column. I looked, this is the way I did it. I said, hey, I look at this column, I said 0, 0, 1, 1, 0, 0, 1, 1. That's a very easy sequence to remember. 0, 0, 1, 1, 0, 0, 1, 1. And then you say, okay, 0, 0, 1, 1, 0, 0, 1, 1. Yeah, you should be able to do that, okay? All right? Okay, let's do the last one, guys. S2, R2. Okay, 0x, 0x, 0x. Okay, 0x, 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 1, 0. I hope it's correct. 0x, 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 1, 0. Right. Okay. Last one. X0, 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 0, 1. X0, X. What the hell? X0, X, X0, 0, 1. Set? Everyone happy with how I got that? Right, you can follow through on the truth table, you can check my work. I can make a mistake. I'm doing this problem right now, live. I'm not copying off any answer, all right? Okay, now, how do we make the groups? I don't think there's many groups possible here, right? And what about this guy? Yeah, there's nothing else, right? All right, so what do we call this? S2 will equal to? S2 will equal to? Oh, yes. Q0, Q1, Q2 bar. And R2 will equal to? Q0, Q1, Q2. There we go. All right. Okay. Okay. Now tell me, guys, what do we do after this stage? Final step. Right? We're going to build the circuit. Now, it's going to take a long time to draw that circuit. Right? Basically, you'll end up with something along these lines, but what's going to be different? Tell me, in comparison to question number 2, right? What's going to be different in your circuit? Yeah, I mean, in principle, the general outlook. And of course, the circuits are going to be different. Firstly, what are you going to change? This is JK, right? What are you going to have? You're going to have SR. How many over there? How many flip-flops? 2. And how many are you going to draw? 3, right? And then what else is going to change? What else is missing? Come on, guys. What else is missing? There's no system input. There's not going to be any system input. So I'm not going to waste my time and draw it. I mean, drawing circuits is something very basic. Now, what happens after drawing? Once you've drawn it, right? Usually, once you've drawn the circuit, what do? You go to the software. You're going to build it in software. You test it in software. Then what do? You build it in hardware, right? You build it in hardware, right? And after that, then there's another step. If you're really into it, there's something called Verilog. Then you code it. There's a hardware description language. There's a way to, you code that circuit up and you deploy it onto a single chip, and then you deploy the chip. You don't deploy large systems. You deploy it on a single IC. Right? That's how it works. That's how the real workflow works. So you start from a problem. Somebody says, I want even numbers. So I don't know if you saw this problem. Let me tell you this, guys. If you can do this problem, we are in week. If you can do this particular problem, question 2, right? Look at question 2, guys. Question 2. Right, so I'll close it at that. Maybe I'll just finish it off. Step 4, draw the circuit. So let's write it out. Step 3 is done. Step 4, draw and simulate the circuit. Guys, do you really want me to draw the whole circuit? It takes a long time to draw. I would rather we do some more problems, because the hard part is coming to this equation. That is the hardest part, right? In fact, actually, the hardest part is going from a worded problem to the state diagram, right? Let me show you question 2. I want you to pay attention to question 2. So I'll close that particular design problem, the one which was 0, 3, 5, whatever, that sequence there. Look at this problem here. I want you to read this problem, right? We did this in the tutorial, so one group would know already, another group would do it this afternoon. Okay, so you've got to design a system in the form of a synchronous binary counter or sequence generator that cycles through even numbers between 0 and 7. So what numbers will that be, guys? Even numbers between 0 and 7 will be 0, 2, 4, 6, right? If the system input Z is equal to 0, the system goes in ascending order. Ascending means go upwards. So it'll go 0, 2, 4, 6 if Z is 0, right? If the system input Z equals 1, then the system follows descending order. So that means it will go the other direction. 6, 4, 2, 0. So opposite direction. So it's a ring. It's a ring counter. Why do we call it a ring? The word ring comes from Lord of the Rings over here, okay? All right. Now, it comes from when you draw the state diagram, you look at it, it's a circle, right? It's a circle, all right? Okay. So it looks like a ring. So that's why they call it a ring counter. It goes in a circle. So then, so there's a system input, and then we say the system has an output Y, which will turn on only if a multiple of 3, is on the system. So basically, when it's 6, then Y will turn on, right? So you look at this problem. If you are able to do this particular problem, any new state must point to the lowest number on the cycle. What is the lowest number on the cycle? 0, right, on the ring. When we say cycle, it means on the ring, right? Then there's some unused states. What are unused numbers? 0, 2, 4, 6 is used, so what are the unused ones? 1, 3, 5, 7. So those will all point to 0, all right? So guys, this is a tutorial problem. If you are able to do this problem in, let's say, a 20-minute time frame, you are fit for the exam, right? You should be able to do this in 15 to 20 minutes. You are fit for the exam if you are able to do this, okay? All right? So please make sure you attempt this problem. And then the rest of the problems are analysis problems, right? There's some analysis problems. So this is all part of your tutorial, which you will be doing, all right? Okay, now, let's have a look at this problem here. So what have we been doing, guys? I'm trying to cover as many problems as possible. Right, so we started off with the problem, an analysis problem. You see this analysis problem? So this is analysis problem number 1, and we did it on, it is on page 12 of our note, which is on Moodle, right? Week 9 and 10 notes on Moodle. We did that problem, right? We did all of that. We did the state table and all that, system input, system output. So this was our very first problem, right? Then we came up with this. Eventually, you end up with the state diagram. In an analysis problem, you finish off with the state diagram, but if the state diagram is depicting some clear behavior, so if it was saying, let's say, 0, 0, 0, 1, 1, 0, 1, 1, and going all in one direction, then you could have said, hey, this is just a counter going from 0 to 3 and then returning, right? But sometimes it's going all havoc, so there's no clear behavior over here, right? Okay, now then what did we do? The next problem which we did was the ABC problem. So this is a design problem. So maybe I call this analysis problem in class, analysis problem number 1, right? This is in class. So this design problem is in class design problem number 1, right? Okay. So with the design problem, we had a question given to us. Then we had this, right? So there we go. We went through the whole thing. Eventually, we went through the Carnot maps. Then we found the circuit, which is very messy. The circuits will be messy, right? The circuits will be messy, all right? Okay. Now, then we went through analysis problem number 2. Okay, it's actually analysis in class analysis problem number 2, but it is question 1 from handout. Question 1 from the handout. Yeah, remember that one? We did this one. Yeah, all right. Then we did, okay, then we came here. Then this is in class problem number 2. So we've done 1 analysis, 1 design. 1 analysis, 1 design. And this is question from week, which week is it, guys? Yeah, week 11, right? We picked this problem up from week 11, lecture 1. Week 11, lecture 1, there we go. So we picked this problem up from week 11, lecture 1 on Moodle. So this is problem number 2. Now, let's move to another analysis problem. And then we'll do 1 more design problem. So we've done 3 analysis problems, 3 design problems. Then we will move to sequence detector, right? So by the end of this week, you should also be on par, and you should finish off problem number 1 in your project. Don't wait till week 13. It'll be too late. It's a big project. It's a 2-week project. So it's a 2-week project. I've given you 1 week to copy from your friend. Okay? All right? Yeah. So 1 week to copy and check with your friend, and 2 weeks to do the problem on your own. All right? Okay? You must always attempt on your own before you copy. All right. So let's do in class analysis problem number, which number is it, guys? 3, right? And it'll be from question 2 on the handout. There we go. This is the one. This is the lucky problem. Guys, let me ask you. So obviously, you know, this is some type of sequence generator, right? As you go through, it will generate some sequence. I mean, look at this one. So how do we display? If you want to use a 7-segment display, you guys know what a 7-segment display is from week 7 or week 8, right? If you want to display this on a 7-segment display, how do we display this, guys? You're going to connect this. This is output 1, output 2. You see, QA is A, output B. You'll connect this to the 7-segment display and it'll show 0, 1. So in our earlier case, we were going to draw a big circuit, right? But you know, because of time constraints, we don't want to, right? So what do? We will connect those 3 things, those 3 outputs, to a 7-segment display and decoder, right? Decoder, and then the decoder gets connected to, the decoder then gets connected to our thing, what do you call, our actual display. You guys remember this, right? Okay, so that's all important. In the project, did I mention we have to connect to the decoder, or you can, okay, so it's open. You can show 4 LEDs if you want. If you want, you can connect a decoder. That's not part of the thing, all right? Okay, so let's go. What is the step 1, guys? Step 1. What is the step 1 in an analysis problem? So what are we doing? I'm continually changing the type of problem you do. You know, how many of you guys go to the gym? Okay, one guy. Wow, it's very strong. Right. Okay. So you know how you go? I don't go to the gym, by the way. It's very unhealthy. Yeah, my gym is KFC. All right. So you go to the gym. You do resistance training on one day, and then the next day you do cardio. Right? You alternate. So this is what I'm doing with you guys. On one day, on one lecture, I am giving you a design problem followed by analysis problem. Design problem followed by analysis problem. All right? So that you guys start to think along those lines, so that you can see the whole picture. Right? Otherwise, you get isolated into one corner of doing only design or only analysis and forgetting about the other corner. All right. So this is an analysis problem. This is our 3rd analysis problem, and we'll do a 3rd design problem as well. Right? We might move to sequence generator. All right. Okay. So what is the first step for analysis? You have to find the flip-flop inputs. So let's trace it now. Let's trace it. What is this JA, guys? By the way, is this in the tutorial? No, eh? Was this in the tutorial last week? No, eh? Different problem. Okay. I try to give different problems. So JA will equal to what, guys? QB. Nice. QB. Set? Good. Let's move to another one. Any other thing that you can tell me? What is JB equal to, guys? JB is easy. X bar. Okay? That's why I'm doing JB first. Always do the easy guys first. All right. What will KB equal to? KB will equal to X XO QA. Yeah, QA. X XO QA. Right? Everyone in agreement with me? Yeah? Okay. Let's look at KA. What do we get here? KA. X bar and QB. Any system output? No. No system output. Right? How do we know there's no system output? Usually system output would be, it'll take the states. So A is the state of QA. So when you will be saying, what will A be? A is the state of whatever the current state is. Right? Okay. What is B over here? What will, if we connect an LED to B, what will B, that LED behave like? It'll light up Whenever the state inside, whenever that flip-flop is storing a 1, that LED will light up. Whenever the sys-flop is storing a bit 0, that flip-flop, that LED will turn off. Right? So that's the idea. Okay. There's no system. Okay, when does system output happen? System output is when you tie these two together into some circuitry again in order to have an output like this. Okay? All right, guys. So, step 1. Guys, I'm going to write it in really short, okay? Ah, man. Right, set. Okay, good work. All right, now, flip-flop inputs. What did we write? What did we catch? We said there is JA is equals to QB. What else, guys? What else? Tell me some more. KA is equals to X bar and QB. JB is equals to plain X bar. KB is equal to X XOR QA. Set? Everyone happy? All right, now next step, step 2. State table. State table. All right. State table. Do we have a system input? X. Do we have a present state? What do we call this, guys? QA and QB? Guys, the order doesn't really matter so long as you are consistent. Your labeling is correct and you're following the same thing. All right. Then what happens after this, guys? Your flip-flop inputs. What are your flip-flop inputs, guys? JA, KA, JB, KB. What happens next? Next state. Oh, this is system input. Sorry, I made a mistake. System input. And this is present state. I saw in the bookshop there's now some pen where you can use an eraser, right? Right. Which side do you populate first? We do so many of these problems that you should become confident with it. Which side do we populate first? This side, right? So the input side, right? This first section you call it, the input section. 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1. Sorry, man. 0, 1, 0, 0, 1, 1, 1 0 0 1 0 1 1 1 0 1 1 1. Rightio. Okay. Now, let's now find these flip-flop inputs using the equations. All right. So what we'll do is I'll take JA, right? These guys here, somebody can take, okay, this half of the class can take KA. These guys here can take JB, right, JB, and you guys take KB, all right? So populate this, all right? JA, oh, I'm JA, JA, KA, JB, KB. So the class is divided into 3 parts, right? Okay, JA. Wow, that's so hard, man. JB, JB, JB is X bar.